Okay, today we're going to talk about some applications for flip-flops. Okay, there are four applications that we're going to talk about. Um, we're going to look at an event detector, a data synchronizer, a shift register, and a frequency divider. Later on, we'll cover asynchronous and synchronous ripple and parallel counters and state machines. All right. An event detector, basically what that is it's capable of detecting and holding a signal until the event that changed the signal can be addressed. All right, here's an example. A door sensor on a home burglar alarm uses an event detector circuit. When someone opens the door, the alarm will go off. Now, if it wasn't for that event detection circuit, the alarm would only go off when the door was open. Then someone can come in, quickly open the door, and shut the door, and the alarm would sound just for a brief time, only the time that the door was open. So that's no good. Okay, here's an example of event detection circuit using a D flip-flop. All right, just quickly looking at the flip-flop, you can see that the preset, and you know that presets are active low. So your preset is hooked to high, so meaning that preset is eliminated. It's not going to work. Okay, on your D input there, you have a 1 just sitting there. Why? Because it's hooked up to VCC. Okay, your clock now is your single event. In this case, for the burglar alarm, it would be the door opening. Okay, so once it receives a high signal, okay, the rising edge of a clock. So once it gets that rising edge, this D now, the one sitting on the D, transfers over and will now output a high signal out of that Q. Hopefully that makes sense. And it's going to continue to output that high signal no matter if the clock goes up or down. Doesn't matter. Why? Because there's always a 1 sitting on that D. Okay, hopefully that makes sense. So the burglar can open and close the door several times. It doesn't matter. It's always going to output a 1. Now, we want to clear that. That's where this clear comes into it. So let's say that you accidentally set off your home burglar alarm. You have a password that you can put in to clear or turn off the burglar alarm. That would be the clear here. So this is an active low, meaning we have to send in a low signal in order for this burglar alarm to finally turn off and output a 0 on the Q. That is an event detection circuit. Okay, here's a timing diagram. You're welcome to look at that. I'm not going to sit here and explain it. Okay, if you understand how clears work, if you understand how a D flip-flop works, then you should be able to understand this. If you don't, you need to go back and look at the presentation that talked about D flip-flops. Okay, a data synchronizer. Now with a data synchronizer, it's basically kind of what it sounds like. Okay, everything's going to be synchronized together. All right. Now, when you deal with combinational logic, that's and, ors, inverters, nands, and nors, and all that stuff, normally you don't really care about timing. Okay. However, because there might be some situations where you want all of your combinational logic to occur or output at the same time, you may use a data synchronizer. Okay. And it's really simple. Okay, it's a really simple concept, and we're going to look at it here in a minute. All right, here's a data synchronizer, and you can see it's a bunch of latches. Okay, and basically all that it is it's a parallel circuit. Okay, which means that this clock travels to the clock inputs at the same exact time. Okay, it's not a ripple counter. So it's going to travel to the clock all at the same time. So think about what you know about a D flip-flop. You know that a D flip-flop will not pull whatever is on the inputs until there's a rising edge. Then once that rising edge occurs, it will transfer over to the output. All right? So what does that mean? Let's say I have a 1, 0, 1 here. Okay. Now, when my clock is on a rising edge, then it will unlatch and allow the data on A, B, and C to pass through and be outputted. So it synchronizes the data all together and unlatches it at the same time. Okay? Again, if you don't understand the latch, you need to look back at a previous video. But again, a latch holds the data until it's ready to be released. And it's released by either the clock or remember we had the enabler. And that's a data synchronizer. Okay, there's the timing for a data synchronizer. Once again, I'm not going to explain it, but you can see how this data is all held together until this rising edge of the clock. Once that rising edge of the clock occurs, then all this data gets transferred out to the outputs. All right, the next one we're going to look at is a frequency divider. We've used frequency dividers before. Okay, and as the name implies, a frequency divider basically produces a digital output signal that's half of the input. Okay, and frequency dividers are always used in asynchronous counters. Asynchronous counters are counters that do not aren't relying on the clock. All right. In all cases, your D flip-flop for your frequency divider, your not D is hooked up to, I'm sorry, your not Q is connected to your D input, okay? And that's so you get a toggling action. In the JK flip-flop, your J and your K inputs are always hooked up to 5 volts. Why? Because when both inputs are a 1, it toggles Q. All right? Again, if you don't understand JK or D flip-flops, you need to go back and look at that. Now, you can see the clock input is half the clock output. So the clock input is twice, there is twice as many pulses as the output. Okay, you can see that in the timing diagram. All right, and that's all that is. All right, when we start getting into ripple counters and things like that, you will see how frequency dividers, it'll start to make more sense. Okay, here's the timing of it. There's all the formulas of dealing with period and frequency and such. You can take a look at that. I'm not gonna explain that. Okay, shift register. It's basically a group of flip-flops, usually 4 or 8, and it's arranged so the values are stored in the flip-flops that are shifted from one flip-flop to the next on every clock pulse. Okay, shift registers are used extensively in digital displays. Think of a calculator. As you type numbers in a calculator, the numbers shift over. This is done by a shift register. All right, shift registers. This may not make a whole lot of sense right now, but eventually it will. Okay, 4 types. All right, serial in, serial out. Think about what a serial is. Serial means one after another, or like a linear. So as data in, data passes from one to the other, to the other, to the other, finally out. Okay? Same thing, data in, to the next, to the next, to the next, to the out. So it's a linear. Alright? So really these two guys are actually the same. Serial in, serial out, and it works from left to right or right to left. That doesn't really matter. Okay? So it is linear, meaning it happens one after another. Now, the next one is parallel in, serial out. Think about what parallel means. Parallel means that the signal is going to go to all of them at once. Parallel in, serial out, meaning now it's going to be linear out. They're all going to go in at the same time, but they're going to come out one at a time. All right? The last one, serial in, so they're going to be linear in, but parallel out. All right? May not make a whole lot of sense right now. We'll do an activity with this, and hopefully this will begin to make sense for you. Okay, so here's a shift register using a D flip-flop. and you can see how it is parallel in. All right, parallel in, because all of the clock occurs, all the clock inputs occur at the same time. All right, and it's going to be serial out. Data in, and the data is just going to go from one to the next, to the next, to the next. All right, so this one's parallel in, serial out. All right, here's a shift register of JK. All right. Once again, you can see how the clock is all parallel together. So the clock pulses happen all at the same time. Okay, a timing diagram. You know how I feel about timing diagrams, but however, you can see the ripple, how the ripple will pass through. Okay, this is a serial. I mean, it has to go from one to the next, to the next, to the next. This is what I mean by serial. Okay, it's linear. It happens in a line. Medium scale integration. Okay. This is a 4-bit shift register. 4 bits means that there's 4 shift registers. All right. I'm not going to explain the whole thing right now, but you have outputs that are both parallel and serial. Okay. You have parallel inputs, which will give you obviously some parallel outputs. All right. You also have serial inputs. You have a mode control, which we're not going to worry about right now. You got a clear and a clock, and your clear is obviously an active low, and the clock is a rising edge. All right. So basically, you can start to understand the medium scale integration. There's 4 shift. I'm sorry. There's 4. Shift registers. That's what they are. There's 4 shift registers inside of that. Here's an example of a circuit, a shift register circuit, and it is not, we're dealing with parallel now, it's dealing with serial. So you're going to have serial in, serial out. Alright, your clock down here, you have a clock pulse. Alright, so on the rising edge of the clock, things will happen. Alright, your data in is right there. So it's going to take whatever data sits on SR on serial write, and it will output it. That's how it works. Finally, shift diagram for this. All right, not going to worry about it. And that is that.